So this is continuing on our discussion of gas laws. So what I want to start this video on is Graham's law. So draw yourself a container and leave an opening in it and draw particles of two different masses. So gas A is going to be the smaller, gas B is going to be the larger, and I am proportionally putting the same amount in there for a reason. So Graham's law is focusing something on effusion. Okay, now you may have heard of the term diffusion. That would mean you're spraying an air freshener in the room. It takes a while for you to completely smell it throughout the whole room. Effusion is gas coming out of a container, okay? So what Graham studied was gas leaving a container, So what I wrote down was Graham's law. Rate of effusion of the same number of molecules at the same temperature and pressure, and this little squiggly is proportional to the speed of the gas molecules, okay? So he saw a relationship between, if both of these gases were in the same container, they'd be at the same temperature and pressure. They are affected mainly by the speed of the gas molecules. And what you need to consider is the speed will be different between A and B because A is smaller. So think about speed of that particle. Now, the law itself is in this format. So the rate of gas A versus the rate of gas B, and it really doesn't matter which one you do, but it makes more sense to set it up this way. Molar mass of B, square root of it, is proportional to the square root of the molar mass of A. So I always put B on the bottom here, the bigger one, because then the molar mass on the top is bigger than this, just so the numbers look a little better. Now, what is rate? Okay, now we're going to spend a lot of time on rate, especially more second semester than first, but rate is going to be some kind of change over time, okay, some kind of change over time. So we may not be able to calculate rate of these gas particles, but we can look at their time and how quickly they leave the container. So I could include time here, but since time is the inverse of rate, essentially, what you're going to see me write over here on the right is the time of B. So B is on top and A is on the bottom. So here it's kind of flipped, and that's because, again, rate is a function of time. This is not going to be anything with a unit. It's just going to be a number. Instead, you're going to have to give a statement for your unit of this. Okay, so you're going to have to say A effuses how many times faster than B. Okay, so how many A effuses how many times faster than B? Because you're comparing A to B here. Okay, so again, A is going to be the smaller one. If you set it up this way, it'll kind of make a little bit more sense numbers wise. All right, so using that, let's try a couple problems, okay? And with all of these problems that I'm doing, I hope that you can stop the video and kind of try them on your own, and then see if it agrees with what you came up with versus what I came up with. And again, this is just how my brain works. So please realize that if your brain works somewhat differently, that's fine. Okay, so I have a container, a sample of unknown gas M, so that's my unknown, flows through the walls of a porous cup. So again, porous means it has holes in it, in 39.9 minutes. An equal volume of hydrogen gas measured at the same temperature and the same pressure flows through in 9.75 minutes. What is the molecular weight of the unknown gas? Again, molecular weight is just another term you sometimes hear interspersed. It means the same as molar mass. There's technically a difference, but we're just going to keep it at that. So I want to put, I don't have rate here, but I do have times, okay? And so I'm going to take how long does M take versus how long does the hydrogen take? And I know hydrogen is going to be the smallest of the two because hydrogen is going to be the smallest thing. I'm going to take the molar mass of M, which I don't know, over the molar mass of hydrogen, which I do know. Okay. So I'm going to take the square root of the molar mass of M, which I don't know, and then I'm going to take the square root of 2 grams per mole, which is the molar mass approximately of hydrogen. And I'm going to set that up versus 39.9 minutes versus 9.75 minutes. So your calculator should spit out a molar mass about 33.5 grams per mole. Okay, so that's just showing you how to use the calculation and how to kind of set it up in your calculators. Okay, so that's the first part. Second part is to find the mole fraction of M, and both gases were in the same containers. Again, we are in the same container. I kind of jumped the gun there a little bit on that, but we know that they have equal volumes, so their volume is exactly the same. We know that they are at the same temperature, okay? And we know that they have the same pressure. So if that's the case, what is also the same, okay, thinking of PV equals nRT, is the number of moles. So that must mean the mole fractions of both M and hydrogen must be the same. Okay. And finally, part C of this problem. Find the mole fraction of M if both gases in the same container flow at equal rates. So what I'm going to do is I'm going to force this. Each time hydrogen comes out, the M gas needs to come out as well. So that's going to make me force the gas to do stuff that it doesn't want to do. So what I have is a relationship between the speed or the time it took to come out of the container. So I could take 39.9 minutes and divide it by 9.75 minutes, and I get a proportion of about 4.09. So what I could do is I could say, okay, the mole fraction of M is going to be 4.9 times the mole fraction of hydrogen, okay? Because I know that because hydrogen flows so much faster, I kind of need to slow that down and speed this up. So that's why I'm going to multiply that by 4.09. I know that every mole fraction in that container is always going to add up to 1. Okay, so however many gas I have in that container. So I am going to take that mole fraction, okay, of M. I'm going to substitute in 4.09 times the mole fraction of hydrogen. So that's really what I'm doing here. Then I end up with 5.09 moles of hydrogen. So I end up solving for the mole fraction of hydrogen as being about 0.196 for that mole fraction. And if I subtract that from 1, I get 0.084 as my mole fraction of M, So this is just an example of kind of using the molar mass and effusion Graham's law to kind of do that. This next problem is going to kind of include a couple of the ideal gas law equations we derived. Okay. So chemical substance NO2 is actually a mixture of NO2 and N2O4 at 45 degrees Celsius, 1 atmosphere. The density of the sample is 2.56 grams per liter. What is the partial pressure of each gas? Okay, so I'm going to pause it and I'm going to show you some of my work. So I'm going to use molar mass is equal to the density times R times T over pressure. So I was given the density, I could find my R, and I have my temperature, and then I have my pressure. Now please notice I did something wrong in my setup. Reason I do this is so that you could see me make the mistake and then you don't make the mistake. You always must have all of your temperatures in Kelvin, 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 okay? Otherwise the kelvins will not cancel when you have your R unit. So mathematically it comes out to be, the mixture is 66.8 grams per mole. So when you plug this all in your calculator, that's what you get. Well, I still don't have the partial pressures of each gas yet, but I do have some information. I know that NO2's molar mass is about 46, and N2O4 is about 92 grams per mole. So I could take that and I could say, okay, my mole fraction of these two individual gases will always add up to 1. So I could always solve for one of the variables knowing that. So what I'm going to say is I'm going to kind of set up kind of a weighted average kind of problem, because this is my overall mass of my mixture. So I know part of it is NO2 and part of it is N2O4. Well, if I know the mass is 46, some proportion of that, and then if I know that the other mass is 92, if I multiply it by 1 minus the molar, the mole fraction of NO2, I could then find my mole fraction of NO2. Okay. So when you plug it in your calculator, you end up with 0.548 and then 0.452 as your mole fractions. But that's not my partial pressures, but I'm almost there. Now realize that I have a pressure of 1 atm. That's the total pressure in that container. So I always do this even though math-wise you don't have to, but just when you look back at your notes, you could see where I got the numbers from. So if that's my mole fraction, if I multiply it by 1 atm, that's the amount of pressure unit due to the NO2, and this is the N2O4. So again, I put that in the notes just so that if you look back on it, you don't get confused and you're like, where did that number, you know, she's just putting ATM next to it, even though this is the mole fraction. So that's why I do that. Part B of this problem, find the weight percentage of each gas. That's talking the mass, okay? So if I know NO2, if I know it's 0.548 of the total, and I know its molar mass is 46, and if I know my total is 66.8 grams per mole, okay, and if I multiply that by 100, I could essentially figure out how much of it is NO2 versus how much of it is N2O4. Well, if you do the math here, you end up with 37.7% is NO2. So then if you just subtract that from 100, you will get around 62.3% as N2O4. Okay, so that's how you kind of do a couple of these problems related to gas law.